Hi, in this video we're going to look at calculating the magnitude and direction of vectors. In the last video we looked at our basis vectors, I hat and j hat, and how we could represent using these vectors and any combination, addition or scalar multiplication of these vectors, we could represent any direction or any vector within two-dimensional space. Now this is great because that means we can represent any vector in two-dimensional space, which means we can do any operation with these things. So if I was to choose a vector, let's say we do a vector, and we say it is 2 in the I direction and 4 in the j direction. This vector in this form, in its component form, encodes information about how long the vector is and also what direction it's pointing in. So today we're going to look at calculating those two things. Let's draw the vector on the Cartesian plane. So it's going 2 across and 4 up. That's our vector here. If I want to calculate how long that arrow is, I can draw a triangle. It's going to be right angled because our axes are right angled. And our magnitude of the vector is just the length or the hypotenuse of that triangle. So if I want to calculate the length of the hypotenuse, we've got, so 16, we've got 20. C equals, we take the positive square root because we're talking about a length. Can I simplify that vector, that surd? I can. We've got 4 times 5. And we've got 2 root 5 is the magnitude of that vector. Now, if you want to, so it's always nice to express it in surd form. You can also give it an approximation. So if I do that, I get 4.47, which you can sort of visually inspect this length here, and it sort of looks a bit longer than 4 long, right? 4.5 approximately. So the way that we're calculating magnitude is by using Pythagoras' theorem. Now you don't need to show this working each time. If I was to represent a generalized vector, so let's look at our vector again. Let's do vector A. Let's say it's going X amount in the I direction and Y amount in the J direction. I can write my magnitude of A, or the length of the hypotenuse. This is my symbol for that. We use sort of the absolute value signs to signify the magnitude of the vector. And this is how I calculate the magnitude. So I just pop it straight into this formula, which is gotten by rearranging Pythagoras' theorem, and we can output the magnitude. So if I was to do another vector, B, let's do one with negative values. Oops. Let's do -4, 2. What that looks like, we've got -4 and 2 up. So we can say our magnitude of B equals -4 squared. Again, the whole -4 needs to be squared. So all of it goes in the brackets, plus 2 squared. We get 16 plus 4 is root 20, which is what I had before. So it also works in the negative direction. That's how we calculate magnitude. Now direction. When we're talking about direction, the default direction is from the positive x-axis. The positive x-axis being this one here. So if I'm looking for the direction of this vector here from the positive x-axis, I'm going around in an anti-clockwise direction, and I want to know what that angle is. The easiest way to determine that is to find the angle made in this triangle here. and then I can use some angle properties to work out what this one is over here. So if I'm to find the angle of this vector, I'm going to draw it on the Cartesian plane below. We've got -4 and we've got 2 up. So we'll draw our triangle here. We want to find this angle in here. We know it's 2 up and it's -4 in the I direction. But when we're calculating angles, we just want to know the length. So the length of that is 4. We want to know our angle, let's call it theta in here. So we can say tan theta equals opposite over adjacent. Inverse tan. And we get 2 and 4. 26.57 rounded to 2 decimal places. So if that's our theta and we want to calculate, let's call it theta 1 in here, theta plus theta 1 make up 180 degrees. So we can say theta 1 equals 180 minus theta, 26.57. And we get 153.43 degrees. So this is how we calculate the angle of the vector. We calculate the magnitude using our Pythagoras' theorem. You don't necessarily, when you're calculating these, need to show all of the working. How I would do it is I would use this theorem straight away with the rearranged form, and I would draw my triangle and enter these straight in. So I'll show you one more on how we can do that. So let's say we had the vector C and it was √3, let's say, and -1 in the j direction. Now √3 is about 1.87, I think, at 1.73. So we've got 1.73 is about here, and we're -1 down. Okay, so this is my triangle here. Now I'm trying to work out this internal angle here. This is 1, this is √3. So when I'm calculating my theta, we've got the opposite is 1 over √3. Now, if you know your unit circle really well, you'll be able to tell me what that is. If you don't, you can just pop it into your calculator, making sure that you enter it as √3 and not the approximation, because then you'll get the exact value and you get 30 degrees. So this angle in here is 30 degrees. However, we want the angle going all the way around like this. So let's call that theta 1. Theta 1 will be 360 degrees, the whole circle, minus our 30 degrees, and we will get 330 degrees, which is the direction of that one. You could then work out the magnitude, so let's quickly do that. The magnitude of C is the square root of √3 squared plus -1 squared, 3 plus 1, which is 2. Okay, and we've got our vector represented in terms of its magnitude and in terms of its direction down here. Whoops. Okay, so that's the video representing vectors in terms of their magnitude and their direction. Hope you enjoyed, and I'll see you for the next one. This video accompanies a worksheet series that aims to develop conceptual understanding with vectors. If you'd like to access the worksheet, click in the description below.